Okay, so you'll be happy to know that this time I'm not going to do a lot of drawing. You usually see me, I don't really want to redo the PowerPoints and just read them to you most of the time. But in this case, it's very visual, and so I'm going to be using the actual PowerPoint to make some points here. Now we're going to start with, now we're going to look at valence bond theory. We have been looking at VSEPR, okay, valence shell electron pair repulsion theory. We're going to look at a few different kinds of theories, and then we're also going to see how we can get multiple bonds, okay, multiple bonds meaning double and triple bonds and so forth. So far we haven't really considered those quantum numbers that we looked at on those atomic orbitals earlier. We're going to bring that into this now. One important thing, though, is when we do covalent bonding, we know we share electrons. Also, the valence electrons in the atomic orbitals have to overlap with the electrons with opposite spins. Okay, in order for a bond to happen, the valence electrons in each atom's atomic orbitals have to overlap with electrons with opposite signs, opposite spins. All right, so far, that's kind of okay. We've done a couple of these. For example, or hydrogen is a 1s1, meaning it has one electron. And so if I make H2 or HH, the s orbitals are spherical, remember, and so they can overlap and each provide one of the electrons' opposite spins to form the hydrogen molecule. We might also have hydrogen, a 1s1, and for example, fluorine, which is, we'll just skip that, 2s2, 2p5 in its valence electrons, and that would be something like this. Okay, well now these two electrons can overlap here. Okay, now fluorine, remember hydrogen is a sphere, and fluorine and the p orbitals of fluorine, where this extra electron is, are shaped like a dumbbell. So we might get something that looks like this. Oops, I didn't mean to have all that, but this dumbbell has got, I don't know, something funky on it. Either way, now our electrons can be in this space where the overlap happens, and one would be spinning in one direction and the other would be spinning in the other direction. Maybe we could do F2. Okay, each F is still configured like, well, let me just draw it. All right, like that. Again, those are from the p orbitals. The overlap is going to be at the p orbitals, so bad, bad, bad. There's one fluorine p orbital, and here's the other fluorine's p orbital right in here. They can overlap into those atomic orbitals in the p's and form that bond. Okay, so that's, we haven't really spent any time thinking about quantum numbers and atomic orbitals and bonding just yet. But now we need to consider that. We've kind of glossed over all those atomic orbitals because it didn't fit our theory very well. Okay, so we need to think about what's wrong with carbon and why we can't form, according to our theory, why these won't form four bonds. Now, we know from experimental evidence that CH4 is a tetrahedral, meaning it has 4 areas of electron density. And we also know other information like it's not polar. So let's think about the electron configuration of carbon for a minute. The electron configuration of carbon is 1s2, 2s2, 2p2. Now, we don't really care about these 1s's because we're only interested in valence electrons right now. All right, so if we were setting up an energy diagram, here'd be our S and here'd be our P's. And S is slightly lower in energy than P's. And so we'd fill our 2 electrons into the S orbitals, and then we'd fill a P orbitals until we reached the number that we need, which is 4 in this case. All right, now given the rule that we have to have overlapping atomic orbitals in order for a bond to form, let's look at what's happened here. We can form 2 bonds, that's all, given this configuration. Right, we could bring in a bond here, an electron here and an electron here from like hydrogen or something like that. But this is filled. I can't get another electron to go in there, and there's no electron here. And so the most bonds we could form in carbon under our theory would be 2 bonds. But we know from experimental evidence that it's tetrahedral. Okay, so that causes some difficulties, of course. So, Linus Pauling suggested basically that when atomic orbitals overlap and bond, they change their shape some. Okay, that's what he proposed as far as atoms and their atomic orbital versus bonding into some kind of molecules. Okay, the shape of atomic orbitals changes in the molecule. So not in the atom, but in the molecule. All right, and that allows us to use another model. Okay, the other model in chemistry, even though models are great and they often explain things, they don't always explain everything. And so sometimes we need a different model to explain more things in order to make it comprehensible. So remember, our earlier carbon was 2s and 2p, where we had a full s and just 2 electrons in our p orbitals. But if we promote these 4 electrons into the 4 possible orbitals, okay, we have promoted one of these electrons, for example, to this one, to this empty p orbital. Now that gives us 4 orbitals, and in this particular case, you'll notice that they have the same energy. This is on purpose. Okay. 1 orbital in this carbon is the same energy as any other orbital in that particular shell. By using these hybridized orbitals, okay, oh, well, I haven't really told you about them yet. By using something called hybridized orbitals, we can find a way to get carbon to have a tetrahedral and 4 bonds. All right, so here's our regular orbitals as atomic orbitals. When we bring these out and we use, we're going to promote one of these to here, we're going to end up with 4 sp3 orbitals. Okay, so we're going to hybridize the orbitals that we have, s's and p's, and form a new kind of molecular orbital here that we call valence bond. All right, so by moving this electron into the p orbital, that gives us 4 sp3s. Now notice, I used not one s, but an s here, and I have 3 p p's, not 3p like in the number n, but 3p orbitals together. That gave us, in the carbon, 4 equal orbitals, each with an electron spinning in the same direction. So that's 4 sp3 or hybridized orbitals that we have available now. Now let's bring in hydrogen, okay, so we can make CH4. Each one of these has an electron, all right, so I can form a bond with the hydrogen by putting that electron the other way in the opposite spin in this hybridized orbital. And so we end up having a carbon with 4 sp3 orbitals. Again, these are about 109.5 degrees apart, just like they would be under VSEPR. What I do want you to notice here is that this sp3 orbital, okay, doesn't have that shape that we might have expected for p orbitals, nor does it have the shape of the s orbital. All right, it has a slightly different shape. All right, so just as a recap, we have covalent bonds. They form when orbitals of 2 atoms overlap, and that overlapping region has a pair of electrons. So they have to have spinning electrons in the opposite direction. And in this case, we have to hybridize our atomic orbitals. On the carbon, we didn't necessarily need to do that on the hydrogen. It was fine as its little sphere. Okay? And of course, the stronger the bond, the more the overlap of the orbitals. So these are the shapes we kind of looked at earlier in Unit 5, earlier in this unit, where this is a sphere for S. We've got 3 possible P's, a PX, a PY, or a PZ, meaning they're on the X, Y, or Z, or axes. We have several d orbitals. This just happens to be one kind. All right, and this is another d orbital, just so you can remember it. We're going to be hybridizing all of these things to form molecules. All right, and so again, we're going to hybridize or change these orbital shapes a little bit in order to make this work for us. So I want to talk for a minute about a really simple molecule, okay, one that we have found is more covalent than non-covalent, and in this case we're going to form BeF2. So if we set up our atomic, our Lewis dot structure with Be, okay, we'd find that we have 2 electrons because it's in group 2, all right, and this would have a configuration of 2s2. Okay, so that would be, here's our 2s, that would be a filled orbital. Oops, that would be illegal. How about this? We'll have a filled atomic orbital. So there wouldn't be a possibility of forming BeF2 in this condition because beryllium is already used up all of the spaces. But this is in group 2, and that means there are still p orbitals there. So we have 2s and 2 p's. They just aren't being used. So in order to make 2 places to bond, here and here, we're going to spread out those electrons into 2 different orbitals. Therefore, we'll have to hybridize an s orbital and one of the p orbitals. Just one. These are unhybridized. I just didn't want that color. But anyway, these are unhybridized, and they're not being used for anything. All right, but we have, when we spread this out, we have 2 new atomic orbitals, s and p. All right, so what we've done is we've used these empty p orbitals that would be like so, only we're only going to use one of those p orbitals, okay, this one here, to mix with this. When we do that, we get this weird looking, very strange looking SP, all right, SP. So we have this kind of a long lobe and a little bitty piece right here. A little bitty piece and a long lobe. Excuse me. So when we bring in our hydrogen, and keep in mind that this just has one electron in it, okay? This is from the beryllium. So keep in mind that when we bring in the fluorine, which, or I guess in this case we've got chlorine here, when we bring that in, okay, it's on the p orbital. That's a 3s2, 3p5, I believe. Of course, there'd be a, yeah, I think that's it. This would come in from each side, and we get this overlap on the chlorine with its p and the beryllium with its two hybridized atomic orbitals. So that would be an sp. We took one s and one p and made two atomic orbitals called an sp. And that allows us to get this bond to form that molecule. All right, so we've already looked at the sp3 hybridization for carbon, methane, well, carbon. In this case, remember, we're taking one s orbital and three p orbitals, not the number n, but the number of orbitals, and that gives us four sp3 orbitals. So we already looked at that, and that allows us to make a molecule like CH4. All right, but I want to talk about when we have molecules that have lone pairs of electrons. Okay, so for NH3, that's going to end up, when you draw your Lewis structure, with one lone pair of electrons and three bonds. Okay, when you do hybridization for any molecule where there's lone pairs of electrons, you're going to hybridize enough orbitals to include the lone pair of electrons. So I still need in my molecule here 1, 2, 3, 4 areas of density. That means I need 4 sp3s, 1 s orbital and 3 p orbitals. That gives me 4 sp3s. And then what am I going to do? I'm going to put in the lone pair of electrons here, and then for each one of the bonds that the nitrogen makes here, it has only one electron. Okay, so those get filled in as well. And then I have room for the hydrogen electron to come in and bond down here in the opposite direction. This lone pair, though, you've got to hybridize enough orbitals in order to accommodate all the lone pairs. So you can see the same thing with H2O. When you draw this, and let's do this according to VSEPR theory, you would end up with a molecule that looks like this. All right, so focus on the oxygen. That's our central atom for a minute. All right, how many areas of density does it have? 1, 2, 3, 4. I need 4 hybrid orbitals. Okay, even though those are just lone pairs of electrons, I need to have those orbitals, and so that's going to give me 4 sp3 orbitals. And notice that the lone pairs of electrons on that oxygen have their own little space, and now I can bring in the hydrogen to fill these, or to bond here to make water. Okay. So, couple of rules, all right. Hybridize enough orbitals to form the bonds and to fill in any lone pairs of electrons on the central atom. you do not hybridize any more orbitals than you need. Okay, so remember when we did beryllium, we got an s and a p orbital, and then there are two p's out here that we didn't do anything with. Okay, all we needed was an s and a p to form two sp hybridals. So don't hybridize anything more than you need. So for everything you need, you take one s and however many p's you need. If you need more than p's, then you take from the d's. And we'll look at some examples of that in a minute. All right, so this little table is in your PowerPoint. I suggest you use it. So far we've looked at linear. Okay, it needs two areas of density. We know that's 180 degrees on the ideal bond angle, and we're going to use two. We're going to have two sp orbitals. We've also looked at tetrahedral, okay, with four areas of density, which we know from VSEPR is about 109.5 degrees. And we have to have four areas of density, one s and three p's. Okay, so we have four sp3 orbitals. And in this case, we have no unhybridized p orbitals. Now, I'm going to go through trigonal planar, trigonal bipyramid, and octahedral relatively quickly here, and then we'll come back. I would suggest you pretty much know these, this little table. It should help keep things relatively straight in your mind. All right, so here's boron. I don't know what we're doing a BF3. Remember, our Lewis dot structure would represent boron as with 3 electrons. There was nothing more, okay? And I could bring in fluorine on each side to do this bonding and form this bond, okay? But I don't have any way when boron, which is 2s2 and 2p1, it could only form one electron unless one bond unless I hybridize. So I need 3 possible areas. I'm going to use the s and 2 of these p's. Notice that one of these p's is left alone. Okay, it's not hybridized, it's just out there. But now I have 3 sp2 orbitals that allows me to bring in the fluorine, cause the overlap, and do the bond. All right, let's look at, in this case, we've got a trigonal bipyramid shape, or molecular geometry, because it has 5 areas of density, right? There's PCl5. Okay, so 5 areas of density. I need 5 valence bond hybridized orbitals. Now, I'm going to use up the s and these p's right away, but that only gives me 4 areas of density. Therefore, that means I need to get 1 more out of the d orbitals. Okay, now the d orbitals are available from period 3 and beyond, so I should be able to do that here. Okay, with p in period 3, I think that's 3s2, 3p3 geometry. Okay, but 3s2, 3p3 means I'd only be able to make 3 bonds in those p orbitals, and I need to be able to make 5. And so I'm going to take 1s, 3 p's, and 1 d to form sp3d. And as you'll see here, that gives you 5 atomic orbitals. 5 sp3d hybridized orbitals. Sure, I didn't want to say something else. No, I do want to say something else. What if I have an I3- molecule? Now, when you draw the Lewis dot structure, you get 22 electrons. So we'll put out the outer atoms, get the octet, and then you're going to end up with 3 lone pairs of electrons on that central iodine in order to get this proper structure. Now we're going to be looking here. This is what we're going to think about hybridizing. It has to have 5 areas. It has 5 areas just like this one did. 1, 2, 3, 4, 5. I have 5 sp3d orbitals. 1, 2, 3, 4, 5. Oh, maybe I have 6 there. What am I going to do about these lone pairs of electrons? I'm going to fill those lone pairs of electrons into the sp3d hybrid orbitals, and then for each bond, I'm going to end up with 1 electron in each atomic orbital spinning in the same direction. Okay, so you always have to account for all of the lone pairs of electrons on this. One more we need to look at, and that's octahedral. Okay, octahedral has 6 areas of density, and therefore I need 6 atomic orbitals. Okay, in this case, I'm going to take an S, the 3 p's, not the number n is equal to 3, but the 3p orbitals, and now I need some d orbitals. All right, so in this case, when I get these 6 areas of density, I'm going to have 6 S, 1 S, 3 P's, and 2 D's to give me sp3d2. That's my atomic hybrid orbital for octahedral things. All right, so in this case, we've got, I think this was SF6. Yes, this is SF6 they've demonstrated for you here. What about if we had TeF5 minus? TeF5 minus is going to need 6 orbitals. When you draw it up, you'll end up with a molecule that looks like this. Put this up here. We end up with a lone pair of electrons down here. Remember, this is our square plane, all in one plane, and this fluorine is extending above. Here's the middle of our plane, extending above the plane, and then this pair would be below the plane. When you set up your sp3s, D2, 1, 2, 3, 4, 5, 6, these are all sp3d2s. You need to account for this lone set of electrons right here, and then every place where you could have a bond. Okay, so in this case, we have 1 lone pair of electrons. We need to account for it in our sp3d2 orbitals. So, coming back to this little table here, we can see that a lot of this follows the same thing we've done in VSEPR, but we had to account for some things that didn't work under VSEPR. This is 180 degrees, and you need 2 SP's orbitals, 2 SP orbitals. Trigonal plane is 120 degrees, and you need 3 sp2 orbitals. Tetrahedral, 109.5, you need 4 sp3 orbitals. Trigonal bipyramid, that's 120 and 90 degrees, those 2 different planes. That means you need to have 5 sp3d orbitals. And for octahedral, all of these are 90 degrees, and you need to have 6 of those. Now, we're going to come back to this unhybridized business in a few minutes, okay? So this will come back into play I just put this here for you to help remember later, and don't hybridize anything more than what you need. So you need a plan, as always. Unfortunately, or maybe fortunately, you can't get away from drawing your Lewis structure. Okay, you must draw the Lewis structure. You can't decide anything if you haven't got that right. Then you can figure out the Vesper shape, how many density areas, how many lone pairs of electrons, etc. And then finally, you can find the hybrid orbitals by knowing the information that you would have had to know to find the molecular shape, not the electron shape, but the molecular geometry shape to begin with. Now I want to talk about how we form double and triple bonds, or multiple bonds. Okay, that's part of this. We're going to use the valence bond theory to help us see these. So some concepts. Okay, any single bond is called a sigma bond. Okay, so every single bond, or every bond, has a sigma bond. When you have multiple bonds, you always have the one sigma bond, and then you have 1 or 2 pi bonds, depending on whether it's double or triple. So for double bonds, you have a 1 sigma and 1 pi. And for triple bonds, you have 1 sigma and 2 pi bonds. Okay. Pi bonds are those unhybridized p orbitals that we were using earlier, looked at earlier, above and below the sigma bond. And we'll see that just in a minute. So remember, this is what we're going to use. The unhybridized p orbitals help us explain double and triple bonds. I guess I'll go on. So let's draw, in this case, ethene. You don't need to know that, but C2H4. So that has 12 electrons, and when we first set it up, we would try to get everything to have an octet, and so you'd end up with a structure as a first attempt that looks something like this. Okay, but this carbon only has 1, 2, 3, or 6 electrons. It has to have 8 to fulfill the octet rule. And so in order to do that, I'm going to move this single pair of lone pair up here, and we're going to form this double bond. Now that gives both carbons the octet that they need in order to fulfill the octet rule. Now that first bond, the one we had over here, this one, that was a sigma bond. Okay, that's the first single bond. Because we need another bond to make this structure legal, that second bond is the p as a pi bond, okay, or forms the double bond. So for C2H4, C2H4. Well, let me go back here for just a minute. No, let's do that here. Carbon, okay, had 3 areas of density. Now that's for each carbon. Let's just look at that. It has 3 areas of density. 3 areas. There's 1, there's 2, and this area over here, all of this is the 3rd area. So if it has 3 areas of density, electron density, that should right away say, well, that is trigonal planar geometry. That also means that that's 120 degrees apart. Okay, so you should right away remember all of those things. All right, and when we were doing our hybridization, we need 3 areas, so we're going to take an S and 2 P's to make sp2. And we'll have to have 3 sp2s. So we're going to take this, this, and this to form our orbitals, our bonds, our electron density. And this is unhybridized. Why is this? Let's put all this back where it belongs. Unhybridized. That's where we're going to get the multiple bond. All right, so in this case, this plane that they're showing you right here, that's your C2H4 in one single bond here between the 2 carbons. All right, and then the unhybridized p orbitals. Unhybridized. Notice that these are dumbbell shape, and I made them really big so we could see them. Each of those is going to end up having the electron, okay? And when those electrons bond, okay, when those electrons overlap, oh, by the way, we get an overlap on the p orbitals. They overlap together, they come closer together, and then each one of these has a set of electrons in them, okay? Notice that this p orbital, or this pi bonding is above and below the plane. There's some up here and some down here, okay? And then there's a picture in your book that tries to show you how the carbons are sp2 right here, okay? And then there's the hydrogen it's bonded to, and this hydrogen is bonded to, okay? But what's left over unhybridized is this, okay? This is your sigma bond. These 2 bonds, when they overlap, are going to be your pi bond, or those 2 p orbitals. This is just another picture of the same thing. Notice that the p orbitals do not overlap here, but as they begin to overlap, they form this pi bond, and the electrons are shared here above and below. They can be above and below the plane. Okay, so there's not 2 sets of electrons above and below. There's one set of lone pairs of electrons, but they float above and below that plane. These are triple bonds. Okay, we're doing C2H2. Okay, when you draw the proper Lewis structure, you're going to end up with a bond, a Lewis structure that looks like this. Okay, now you have a sigma bond. Just this bond is your sigma bond, even though we don't care about these but sigma bonds, but that's a sigma bond, sigma. One single bond. And then these other 2 bonds are 2 pi bonds to make that triple bond. So what happens here? Here we have, they've tried to do this in different colors. So let me focus on red here. Here's one 2p orbital. And then in the black, here's the other 2p orbital on one carbon. All right, and as the 2 carbons bond together to form that sigma bond, then these become closer and closer together. And notice, okay, here we have these dark p bonds. Notice that there's one above and one below. All right, but we also have these red pi bonds, and that also has one above and one below. So we have 2 areas of pi bonding there. They all overlap to make a strong bond, and that pulls the bond lengths and bond strengths, makes the bonds length shorter as they get pulled closer together, and the strength gets stronger as there's more and more orbital overlap on all sides of that molecule. let me see. All right, now I do want to point out one more thing about carbons, sigma bond, really about sigma bonds and pi bonds and how they limit rotation. But we're going to use carbon for just a minute. So let's assume, and I don't expect you to draw this, but let's assume we have a propane molecule. All right, looks like so, propane, like so. Now, if I was putting together a structure and I use my molecular model kit, I'm going to have an upward tilt this way towards my CH2. So that's, let me redo this for just a second. Let's make this dark black and this one green, just so we can tell the difference here. All right, so when I begin to draw this CH3, okay, that first carbon, that second carbon can go up this direction, or the second carbon will go down in this direction. There's rotation around these things. Oops. What am I doing? I guess I don't know what I'm doing. Both of these should have been in red. These are the middles. There's rotation around these angles. Okay, so these bonds can rotate. I can get it in one direction. I can get it to go up. Or, in another second, the bond may be going down. Let me put in our CH3s. So we could have a CH3 this direction, or we could have a CH3 in this direction. All right, so those bonds rotate between the carbons and the carbons. What happens when you have something that's a pi bond? For example, let's go back to our ethane that looks like this. That pi bond prevents the rotation, and this is always going to be in a plane. Okay, so there's no rotation between the carbon and carbon atoms. That later is going to be important to you if you go on in chemistry, and it probably is important for your next exam. I think that's it.